Okay, now let's think about combinatorial library. If this is the first time you hear about this term, combinatorial, you may be curious about what is combinatorial library. Let's say if you have a component A, component 1, and component B, and if your product is combined molecules, then this is one component and the other component and made combination into this product. If this chemistry can be repeated to different components, let's say you can make this component 1 into different structures, and the component 2 is also different direction, but the coupling chemistry is the same. By combining these two combinations, you can make huge numbers of molecules using exactly same chemistry. So first of all, library is collection of many different molecules, and combinatorial library is the library which was made by combination of components. So that's why if you develop one chemistry, the same chemistry can be applied to making out many molecules. If your component 1 is, let's say, 10 component, and component 2 is another 10, how many combinations can you make? At a 10 by 10, you can make easily 100 compounds. If you are making three-dimensional combichem, then 3 components can be prepared and you can build this kind of molecule. This is similar to this kind of a cubic. Then you can expand one direction, two direction, and another direction here. Now in this case, each component is 10 by 10 by 10. How many total product can you make? Yeah, that's 1,000 molecules. So if you think about the speed of synthesis you can do, if you can build 1,000 molecules very quickly, then the very high potential you can apply to your studies. Once you learn this kind of a combichem technique, then next question would be, what kind of molecules you would like to make? Inside the cell, if you add your small molecule, what can be your molecular target? In most of the cases, your target would be proteins. And what is the protein composed of? Protein is made by different connections of amino acids, right? Then small size of amino acids we call peptide. Then your target is made of 20 different amino acids. Then most likely the interacting partner also can be made of this amino acid structure. Then obviously your first choice can be, maybe you want to make a peptide library. So in the sense, if you make this oligopeptide, let's try to count how many combinations you can make. The hint is your building block for peptide making is 20 amino acids, right? Then if you make dipeptide, 2 amino acids connected together, how many combinations can you make? That's a 20 by 20, it's a 400. Only very small dipeptide, still already you have 400 the peptide structures. How about the tripeptide? How many tripeptide can you make? That's a 20 by 20 by 20, that's 8,000, right? How about the tetrapeptide? It's 160,000. How about the pentapeptide? Pentapeptide now is already above million. Now you have 3.2 million different peptide structures. Hexapeptide, it's a huge now, 64 million peptide you can get. Now let's think about the molecular weight of this pentapeptide. In the class that we said the average, the molecular weight of one amino acid, do you remember? It was about 120. Then if it is a pentapeptide, what can be molecular weight? It's a 600, right? So 600 is a little bigger than the Lipinski rules rule of 5. Still, 600 is not too bad. So then, if you target to make a pentapeptide, your library number is already more than million. So if you can make million molecules, that's maybe more than enough you want to try, isn't it? Then this number you can compare with the DNA combination number. Do you remember how many combinations you could make with 10 mer of DNA? Or how about the 20 mer? So this DNA RNAs, they have only 4 building blocks, and then you can compare to make hexapeptide amount of the diversity. This was already 64 million, right? Then how many lengths of DNA or RNA you need? So this question you will see in the next classes, the quiz one. Let's try to make peptide. So to make a peptide, you need to have one amino acid and then another amino acid. So first amino acid is alanine, second amino acid is phenylalanine, right? So if you want to combine these two, now we have two reaction, the functional groups. So one is the amino group and one is carboxyl acid group. So amino group and acid group, that's why we call the building blocks of the protein, we call amino acid. Now let's just say we wanted to make a couple here, and then alanine, phenylalanine dipeptide we want to make. But if you mix these two molecules in the solution phase chemistry, then your end result can be not only alanine, phenylalanine, it can be reversed order, phenylalanine and alanine. So this amino acid and this carboxyl acid can react, make this product. Is that all? Actually, you can get alanine-alanine or even phenylalanine-phenylalanine homodimer you can make too. If you do not control the reaction carefully, not only dimers, now it can grow further. So you may have huge amount of different, very complicated mixtures you can get. So if you want to get very highly pure product, you don't want this kind of a messy reaction conditions. So most of those cases, we use so-called protecting groups. You block one side, and then another amino acid block the other side. Then only this side and this side is open for reaction. Then you can get, in principle, only one product. Exactly the same idea of a protecting other group approach can be utilized for solid phase chemistry. Let's say we have amino acid, one side is protected. Then we can load this amino acid onto the resin. Usually this resin is made of polystyrene and size is about 100 to 200 micrometer size, and we call this either resin or bead. As one side of this amino acid is attached directly to the resin, that's why this side has the same effect of a protecting group attached to the situations. Here if you remove this protecting group, now this is ready to react with another amino acid. This amino acid has open end here, and this one is open end here. Then they can react only one side here. And then you can remove these protecting groups. Then if you cleave off here, you can get expected only a single molecule as peptide. Same approach can be applied to multiple reactions. Let's just say you have resin. Now you add the first amino acid load onto the resin and then deprotect that protecting group, and then you can load second amino acid and then deprotect, load, deprotect, load, deprotect. If you hear me, it's kind of a repeating procedure. The amino acid can be prepared as a one side protected. That means if you have 20 amino acids, only one side, either amino group or carboxylate group, you can protect only one side, and then repeat these reactions on solid support. Load, deprotect, load, deprotect. If you repeat these procedures, that means you can easily automate this procedure. After you make all of this compound, after you finish these reactions, then you can clip off this peptide from the resin, then you can get purified the peptide structure in solutions. So this is the power of solid phase chemistry. Let's check this dipeptide synthesis again. In this case, if you use resin-loaded amino acid 1 equivalent and then solution amino acid another 1 equivalent. So this is a 1-to-1 reaction. And if your reaction yield to make this peptide bond is 90%, what is your end product? At the end of those reactions, you keep these resins and then wash out all soluble materials. Then you have these materials together in the resin. Then you have a 90% of a right product. The problem is 10% of your leftover starting material still can contaminate your samples in final product. So this is not what you want. That's why in solid phase chemistry, you need to use a little more excess amount of this solution phase reagent. So practically, you have one equivalent of resin-bound material. Then you need to add either 3 equivalent or 6 equivalent. If the reaction yield is not very high, then you can push those reactions maybe by adding 10 equivalents. Then the reaction happens. At least, even though the one-to-one reaction yield is only 90%, if you add excess amount of this soluble agent, you can push those reaction equilibrium to the product direction. After you wash out all those leftover reagent, at least on the resin, those product purity can be much higher, maybe 99%. Then you can get quite a pure product from your resin. Then if you remove this, then you can add next step of reagent also large excess amount and repeat this reaction again. Deprotect and add your reagent and wash out, deprotect. This step you can repeat. That's how you can get very highly pure product from your resin reactions. This solid phase peptide synthesis has been invented by the chemist Merrifield, and he got the Nobel Prize long time ago, almost half a century ago. And this method has been established and also paved the way how to synthesize peptide and also DNA utilizing this solid phase chemistry. Make those biological study is super easy. This approach can be applied not only to the linear peptide. This can be applied to globular shape of small molecule synthesis too. So let's say if you load your core structure onto the resin, then you can add one component, large excess amount, and wash out, and the other component, and also wash out, and third component for different position and wash out. And then eventually you can make pure compound. Now this is three-dimensional library. You have one component, two components, three components. It's not linear. It can be globular shape of molecules you can make. And utilizing this type of peptide synthesis similar the approach, millions of molecules have been synthesized utilizing this solid phase combinatorial chemistry. So this is one example. Your final compound is this type of triazine compounds, which has a 3 component. And the chemistry is you can load one component on the solid support, and then second component can be applied on solution phase. And then if you combine this together, now two-dimensional library, and third library can be applied here, and they eventually cleave off here, then you can get this three-dimensional library. If you have R1, R2, R3, each 100 of them, 100 by 100 by 100, you already can get millions of molecules out of this approach. If you want to claim, I made new compound, and I wanted to report this in maybe Journal of Organic Chemistry, you need to prove 2 things. One is identity of the compound, and the other one is purity of the compound. So we are going to discuss what is the good criteria or methods to prove your purity and identity in the class later. If it is a small numbers of molecules you made, then you can do this analysis very carefully for each of those molecules. But if your format of those molecules synthesis is combinatorial synthesis, and if you made thousands of them or millions of them, now characterizing each individual compound is too much burden. So in that case, still you need to prove those identity and purity, and standard method for this is utilizing LC-MS. So first part of the LC usually combined with the absorption spectra, and then it can give you the idea of purity of this molecule. And then second step is injecting this molecule into mass spec and then at least those molecular weight of those molecules. This can give you the idea of this molecule's identity. In this solid phase chemistry, you may have noticed that at least extra 2 steps of reaction is required. The first one is loading of your scaffold onto the resin. And second one is at the end, you need to cleave off the compound from the resin into the solution. 2 extra steps are always required. So this is one approach of solid phase chemistry. There is another approach to remove these extra steps. So in approach 2 of the solid phase chemistry, now here we utilize one scaffold in solution. And then resin-bound reagent we can use. In this case, to react this core structure with this resin-bound reagent, then we can get pure compound in solution and all the leftover resin-bound agent and also side product on solid phase the material. Then by filtering, we can only collect the product and then remove all resin-bound materials. In this case, how many steps of reactions? There is no loading or the cleavage. So core structure was in solution, and then product is also in solution. Reaction was done only one time, and we could collect directly the product. Only one step of reactions. We removed those 2 extra steps. This reaction can be repeated by passing through another resin-bound reagent, and we can get second diversity we can introduce, and even third diversity also we can introduce. We can make a 3-dimensional library, but each reaction is 1 step, 2 steps, 3 steps. No other extra reactions required. So this is almost similar to purifying the water. So in your home, if you have a water purifier, you put your water in the beginning and pass it through, and you can get pure water. Now, one thing you need to consider is always one side should be excess amount. In approach 1, we loaded core structure onto the resin and utilized the excess amount of reagent in solution. And that's how we push the reaction to almost the completeness on solid support. In this case, we took opposite approach. We used a small amount of starting material and large excess amount of a solid phase reagent, and then we got product here. Because of those excess amount of resin material, we can push the reaction to the almost completeness. In this case, if only the starting material is used up to make a product, then you can secure the purity of your material in solutions. And in this case, you can consider resin-bound reagent should not be expensive. If it's expensive, then you cannot use 10 times excess amount for these reactions. So this approach 2 is ideal the reactions for expensive starting material and relatively cheap the reagent on solid support. Then you can get your product quite quickly. One approach for this is utilizing this sphingosine as a starting material and then isolating agent on solid support and then generate this ceramide library. You can load these acyl groups on phenol the resin. In this case, with this electron withdrawing group here, this is activated ester. Then this amine group can attack here and then generate this amide bond. So this is very simple reaction, but the key point here is sphingosine is quite expensive material. A very small amount of sphingosine can be added, and then once this sphingosine is converted into ceramide, then you don't need to purify your product. Collect those material by simple filtrations. Practically, this could be done within a couple of weeks. Very quickly, you can collect this kind of molecules. Here is another example for solid phase chemistry. So previous library was amide bond the library, but here is sulfonamide the structures. So amide is quite popular or the very common the functional groups in biological molecules, but sulfonamide is also very popular in drug compounds. So here is a Viagra, very famous compounds, and Celebrex is a super aspirin molecules. Many of those famous molecules has this motif. Chemically speaking, this sulfonamide should be very similar to amide bond formation, but actually the reactivity of amine group to sulfonyl chloride is not as reactive as amide bond formation. That's why the previous approach 2 was not successful here. One possible reason for that is, in approach 2, one side of the reagent was in solid phase. That was activated the ester on solid phase, usually heterogeneous reactions. That means one reagent in solution and the other reagent is on solid support. Usually the reaction speed is slower than homogeneous reactions. So then if you mix together two reagents in the same homogeneous solution, then reaction speed can be faster. Now to overcome the problem of approach 2, another approach here. You can add one reagent and another reagent here, and one side is large excess amount and then the other side is a small amount. Then you can push those formation of this product is almost a completeness. After this reaction is done in solution. That's why you don't have a problem of heterogeneous reactions. After your reaction is done, now your trick is you add solid phase material here. Now this is another resin material, but which can capture only leftover this reagent. Then this is your on solid support now. Then you can filter off. Here is one real example. So to make this sulfonamide library, let's say we do a coupling of an amine group with a sulfonyl chloride group reactions. And then the product can be this amine group attack here and then forming this sulfonamide as a product. In this case, if you utilize this solid phase bound amine group, this amine group can attack this sulfonyl chloride, can attach this reagent onto the solid support and then filter off. So in this case, which reagent do you think you need to use large excess amount? Amine group or sulfonyl chloride? Yes, you should use large excess amount of this sulfonyl chloride group, and then small amount of amine can react with this and then form up the product. Excess amount of leftover sulfonyl chloride can be removed by this solid phase reagent. Now this reagent has been used as cleaning reagent. That's why this reagent is called as scavenger reagent. So difference from the approach 2 is, in approach 2, the solid phase bound reagent was actually providing building blocks or the component of those reactions. In this case, this reagent only provides the role as scavenging role. That's why this reagent is called as a scavenger reagent. So in this case, you can utilize, let's say, 20 different sulfonyl chloride and also maybe with 50 different amine groups. Then you can easily build up maybe 1,000 of sulfonamide libraries. Sulfonamide is, as I said, the key functional groups for drug compounds and good source of biological materials. Now if I summarize those three approaches of the solid phase chemistry, first one was you utilize a resin as solid supporting material and you load your core structure and then modify your core structure on solid support, and for each steps you need to add excess amount of solution phase reagent. After you are done, you cleave off your product at the end. So this method, the approach 1, should be most common solid phase approach for synthesis, but one of those issues is you need to have 2 steps of additional reaction you need to do. To overcome this problem, approach 2 was you utilize core structure in solution and excess amount of a solid phase reagent. So amide bond formation was the example. And third step is similar to the second step, but third step case, the solid phase reagent has been used as scavenging function. So that's why using scavenger resin is approach 3.